Hi, this is Wendy Penn presenting the third lab report of Physics 2211 about black hole. And for this lab, we're going to analyze a unique star trajectory to find the net force on the star for all points in a dataset, estimate the mass of the black hole, and use data to determine initial velocity to avoid crashing by simulating the motion of a spaceship. So these are some important physical principles in this lab. Firstly, Newton's second law, and specifically we'll be using F net equals dp over dt. And in this lab, we're also focusing on the parallel and perpendicular components, which sums up to be the net force. The parallel component indicates the change in momentum, and the perpendicular component indicates the change in direction. Then, since we are simulating motions between stars, we will be using the gravitational force formula, indicated by Fg equals negative g constant times the two masses over the square of the magnitude of the radius between the stars, then times r hat. Using this can help us to derive an important equation for part 1, which is at the bottom. And it's calculating the mass of black hole, which is equal to the net force times the square of the magnitude of the radius over g times mass of the star. In part 2 of the lab, we'll be using velocity and position update formula, where Vf is equal to Vi plus F net over mass times delta t, and Rf is equal to Ri plus average velocity times delta t. So in part 1, we're tracking the star's motion to find the net force on the star, and given the mass of the star, to estimate the mass of the black hole. Delta T is 86,400 by multiplying 24 times 60 times 60 to find the number of seconds in a day. Here's the actual iteration. We'll use the formula momentum times the formula momentum equals mass times velocity to find initial and final momentum vectors. Delta V is calculated by subtracting V final by V initial. Delta P is calculated by subtracting P final by P initial. dPdt, which is then delta P divided by delta T, which is also equals to the net force. Next, calculating the parallel component of the net force. P hat is the normal vector of P initial. Then calculate the difference of magnitude of momentum over time, and multiply this with the p hat, we get the parallel component of the net force. Then, since parallel and perpendicular components add up to the net force, we can set the perpendicular component of the net force to be equal to F net, which is dp dt minus dp dt parallel. Lastly, to calculate the mass of the black hole, we apply the formula back in the formula slide, and we need to average the mass of the black hole to get a final estimated mass. So I have some variables to count it, and later we can use them to average. And then here's the result. The simulated magnitude of F net is 9.6 times 10 to the 28th newtons. For the parallel component is 4.1 times 10 to the 27th newtons, and for the perpendicular component is 9.6 times 10 to the 28th newtons. The mass of the black hole is calculated by averaging the simulated mass in each time step, which is 1.84 times 10 to the 34th kilogram. And some of the key points to notice in this part: the star follows an elliptical orbit. As it gets further away, less gravitational force and magnitude is acting on the star. And the parallel component indicates the change in momentum, and the perpendicular component indicates the change in direction. And some possible errors are rounding errors. And then moving on to part 2 of the lab, where we need to determine the initial velocity of the spaceship to fly around the black hole without crashing onto the planet or the black hole. These are the initial conditions. The mass of the black hole comes from part 1, and I set a random speed. This is got from trials and errors. And then the actual iteration. The main formula used here is the gravitational force formula, as we need to find radius between various objects and then calculate the force by also having the masses of the objects. For example, the first part, we first find the radius between the planet and the black hole, then apply the gravitational formula by having negative g times the mass of the black hole times mass of the planet divided by magnitude of the radius squared times the unit vector. On the right side, I also apply the velocity and position update formula to move around the spaceship. This is the result of the simulation. The ship is now 1.35286 times 10 to the 11th meters away from the black hole. And then some key points to notice: the initial velocity I have is negative in the x-axis and then positive in the y-axis, so it's moving left and up. And then again, as it moves further away, there's less gravitational force in magnitude acting on it. And then the spaceship spits out as it is closer to the black hole due to gravitational force, and eventually the speed gets big enough that it escapes. And then again, the possible errors are rounding errors, because this lab only uses computational models, so there are less human errors. And then for for this discussion question, in the formulas, Fnet is technically equivalent to dPdt. However, dPdt can be calculated with the star's initial velocity and mass, while Fnet cannot be directly calculated without knowing the mass of the black hole. In the lab, we infer that Fnet equals dPdt. And then this is, again, by trials and errors, the initial velocity I found to create an orbit. And yeah, thank you.